In this video tutorial, we'll discuss the importance of the harmonic order and show you how to determine the harmonic order in a SimRF circuit envelope simulation. We'll be assuming that you're already familiar with building a circuit envelope diagram and setting up a circuit envelope simulation. The harmonic order can be set in the configuration block of the SimRF circuit envelope diagram. The harmonic order determines the total number of simulation frequencies based on the fundamental tones, and it is a key parameter for circuit envelope simulation. It has an impact on the accuracy of the results and on the simulation time. As a user of circuit envelope, you might be asked to manually determine the harmonic order in order to find the most suitable trade-off between simulation speed and accuracy. Let's look at a simple example consisting of a cascade of a mixer and an amplifier with nonlinear behavior. In this example, we have two fundamental tones, the carrier of the input signal determined by the input and the carrier of the local oscillator. When you first set up a circuit envelope simulation, it is recommended that you leave the checkbox Automatically select fundamental tones and harmonic order enabled. Notice that you can select a different harmonic order for each fundamental tone in the simulation. The circuit envelope solver determines the fundamental tones based on the signal sources. After this, the circuit envelope solver determines the harmonic order based on the blocks in the diagram and the carriers required by the output ports. With the default configuration, you can be sure that the desired carrier selected on the output port will be part of the simulation frequencies. In our example, the automatic setting will determine two fundamental tones and a harmonic order equal to 5 for a total of 121 simulation frequencies. You don't have to manually compute the mixing products to perform the simulation. To verify which simulation frequencies are analyzed, you can inspect the pane view in the configuration block. The total number of simulation frequencies has an impact on the accuracy of the simulation. This is because the overall energy is conserved, so if few simulation frequencies are used, all the energy of the signal is folded in the computed envelopes. With the default settings, the harmonic order is determined with a conservative approach that delivers correct results in mildly nonlinear conditions. In our example, if we perform the simulation and inspect the time domain waveforms, the impact of the saturation is visible in the output signal. You can inspect the results of circuit envelope simulation in the frequency domain as well. For example, let's run the simulation assuming that the input signal has a constant envelope. Actually, given that the envelope is constant, we do not need to perform a time domain simulation, and we can simply set the stop time to 0. In this case, the circuit envelope simulation is simply reduced to a static harmonic balance analysis. We can also visualize the impact of a time-varying signal amplitude in the frequency domain and determine the harmonic order to achieve correct results for a given peak power. This setup helps us validate the results and the choice of the harmonic order. Harder nonlinearities and larger signals will require a higher harmonic order. By looking at the simulation results in the frequency domain, you can get an estimate of the correct harmonic order. If the energy of the generated harmonics is evenly spread in the spectrum, you have chosen a harmonic order that delivers correct results and that is a candidate for further reduction. In this test bench, we are simulating two identical RF chains. The top part of the model uses the default settings for the harmonic order. We can validate that the result is correct by increasing the harmonic order at the cost of a slower simulation. We can also verify that if we reduce the harmonic order, the simulation will be faster. Depending on the amplitude of the signals and the nonlinearities of the models, the results might deviate. In this case, a harmonic order of 3 still delivers reasonable results. If your blocks are purely linear, you can perform the simulation with a harmonic order of 1. In this case, as we have nonlinear blocks driven into saturation, a harmonic order of 1 delivers incorrect results. Let's now increase the amplitude of the input signal by a factor of 4. If you run the simulation with default settings and with higher harmonic order, the results are in agreement and show the extreme effect of saturation. Notice that the computed harmonic order is not affected by the amplitude of the input signal. In this case, the harmonic order of 3 produces different results from the results obtained with a higher harmonic order, as the error introduced by a lower harmonic order is in the range of 1%. In this tutorial video, we've seen how you can rely on the automatic choice of the harmonic order and as an advanced maneuver, how you can tweak and tune it manually to find the most suitable trade off between simulation time and accuracy. Results can be validated in the time and in the frequency domain with the given nonlinearities and test signals.